So far, we've introduced Bayesian networks and talked about how to perform inference in them. In this module, we'll turn to the question of how to learn them from. So recall that a Bayesian network consists of a set of random variables. For example, I have cold, allergies, cough, and itchy eyes. The Bayesian network also comes equipped with a DAG, specifying the qualitative relationships between all these different variables. Quantitatively, however, the Bayesian network defines a set of local conditional distributions over each variable xi given the parents of I. And in this example, we would have probability of C given parents, which are none, probability of A, probability of H given its two parents, C and A, and probability of I given A. So finally, if we multiply all of these probability distributions together, then we get what is the joint distribution over all random variables. In this case, we have C, A, H, and I. Then there's a question of how you do inference in Bayesian networks. So inference, remember, you're given a Bayesian network, you're given some evidence that you observe, for example, H and I equals 1 and 1 over a subset of the variables, and then you're given a query variable, which is something that you're interested in. Let's say you're interested in cold. And the inference algorithm is going to produce a distribution over your query variables conditioned on evidence. So for every possible setting of the query variable, we have a probability. So we saw many ways of doing this, including manually by exhaustive enumeration. We can convert Bayesian networks into Markov networks and do Gibbs sampling. And then for HMMs, we have specialized techniques such as the forward-backward algorithm and particle filtering. So inference assumes that all these local conditional distributions are known. But the big question is, where did all of these come from? So all of these numbers are called the parameters of the Bayesian network, the red question marks. And in general, we might not know what they are. So let's try to learn them. So again, in all learning tasks, we start with the data. So in this case, the training data is going to include examples where each example is a complete assignment to X. So this is the fully supervised setting, which is the simplest one to start out with. And then the learning algorithm is going to produce parameters. And the parameters are exactly all these red question marks. These are all the local conditional probabilities. So we're going to go through a bunch of examples and then later show a general principle that ties all of them together. So you might be feeling a little bit that this might be very challenging because probabilistic inference assumes you know the parameters, and it was already pretty hard, both computationally and perhaps conceptually even. But it turns out that for Bayesian networks at least, somewhat surprising, if you're learning under fully supervised data, learning actually turns out to be surprisingly easy. So let's begin. So suppose you're developing Bayesian networks to model how people rate movies. So let's start with the world's simplest Bayesian network, which has one variable, R, which represents the rating of a movie. So the joint distribution is just P of R in this case. The movie rating can be 1, 2, 3, 5. So first we have to identify what the parameters are. So the parameters here, theta, is just the probability of 1, probability of 2, probability of 3, probability of 4, probability of 5. There are 5 parameters, and if you're a little bit clever, you only need 4 of them because the 5 numbers have to sum to 1. But for the sake of simplicity, let's just say that there's 5 parameters. Okay, and now you're given some training data, some ratings from users. You have a 1, you have a 3, you have a bunch of 4s, and 3 5s. And now the question is, how do you estimate the parameters given the training data? Let's just follow our nose here. Well, intuitively, you would think that the probability of a rating is proportional to the number of occurrences of that particular rating in the training data. So now this is just intuition. It might be a good thing or it might not be a good thing. Well, let's find out later, but let's just go with that for now. So here's the training data, and what I'm going to do is the parameters are this probability table. So we're going to see a lot of these over the course of the next few slides. So for every rating, I'm going to count number of times it shows up. 1 shows up once, 2 shows up 0 times, 3 shows up once, 4 shows up 5 times, and 5 shows up 3 times. And now I'm just going to sum up all the counts. That gives me 10. And I'm going to normalize to get my probabilities. And that's the probability estimate. That's it. Count and normalize. Okay, so let's level up a little bit and talk about two variables. Suppose that now the rating is governed by the genre. So in particular, the Bayesian network is you first generate the genre, and then you generate the rating given the genre. So now there's the parameters of this Bayesian network includes both the probability of the genre, which can 2 parameters, and the probability of rating given genre, which includes 2 times 5 parameters, so 10 parameters for a total of 12 parameters. Again, if you're being clever, you can get that down to 9. So now we're giving some training data. So we have each training point, remember, is a full assignment to all the variables. So we have G equals D and R equals 4 here. So now, how do we estimate the parameters given this more complicated Bayesian network? So following our nose again, there's an intuitive strategy is that we're just going to estimate each local conditional distribution separately and see what happens. Okay, so what does that mean? That means for probability of G, I'm just going to count the number of times particular values of G show up. So D shows up 1, 2, 3 times, and C shows up twice. So notice that this is the kind of same calculation as we had before. So now this is 3 fifths and 2 fifths if you sum up and normalize. Okay, so in estimating P of G, I simply only look at the slice of the examples that matter for this. And same with probability of R given G. So now I'm going to look at all the possible assignments to the parent of a particular node and also that node. So that's a G and R. So D4 shows up twice. D5 shows up once, C1 shows up once, and C5 shows up once. And now I count and normalize, and I get my probability estimate of R given G. Okay, so far so good. So in summary, consider each local conditional distribution separately, and then count based on the slice of the data that matters and normalize. So now let's consider 3 variables. So we have a genre, whether the movie won an award or not, and the rating. So here we have a genre and whether it won an award, influencing whether how well the movie is rated. Joint distribution is P of G, P of A, P of R given G and A. So now we have local conditional distributions for each of these factors here. So remember that these structures, this type of structure was really special in Bayesian networks. It gives rise to explaining away. It's a thing that if you marginalize unobserved leaves, you render things independent. And it was really a hallmark of Bayesian networks. But from a perspective of learning, there's really nothing special here. And to see this, what we're going to do is just, suppose we have some training data, which includes assignments to all 3 variables. We're just going to count and normalize again. Okay, so here we're going to start with P of G. This is exactly the same thing as before. We just look at only the genre. And then we're going to look at P of A, which is analogously looking at only 0, 1, 0, 0, 1, and counting and normalizing. And now the big local conditional distribution is P of R given G and A. So here I'm going to look at the parents of R and R itself. I'm going to count the number of times this local configuration happens. So I have D01, showing up once, D03 showing up once, and D15 showing up once, and each of these showing up once. And now I want to normalize, so I have to be a little bit careful. I don't want to add all these numbers and normalize because this is conditioned on G and A. So that means for every G and setting of G and A, I have my distribution over R. I'm going to look at D0. So I have R, one occurrence of R equals 1 and one occurrence of R equals 3. So that's, if I normalize that, it's going to give me half and half. And now for this setting G and A, I only have one possibility of R, so that has probability 1, and same for these other ones. So again, everything is count and normalize, where you have to pay attention to what you're normalizing over. You're only normalizing over possible values of R, not G and A. So one thing you might note is that a lot of these probabilities are 1, and the probabilities that are not mentioned here are 0. So you might wonder that if this is a good estimate, but we'll come back to that later. So now let's invert the V structure. Let's look at a different structure. So we have the genre, and suppose we have two people, Jim and Martha, and they're both going to rate this movie, and both of them rate it depending on the genre. So G generates R1 and G also generates R2. So now we have this 3-node Bayesian network, and the estimation is going to be the same. I'll just go through it very quickly. So we have parameters, 1 for every variable here, and so probability of G is count and normalize. Probability of R1 given G is you count and normalize. Again, remember that I'm normalizing over possible values of G. So you can partition the rows based on the value of G. So here I have 2 and 1, and I'm normalizing 2/3 and 1/3. And G equals C is just handled separately in a separate normalization. And then R2 given G is analogous, so I'm not going to go over this. So this is fine, except for what I'm going to now do is think about the setting where suppose you have not just 2 users, but 1,000 users or 1,000,000 users. Now, you might be a little bit worried because now for every user, you might have to have their own local conditional distribution. And the number of parameters might just blow up, which means that estimation might be hard, especially for new users. So we're going to consider a slightly different model. It's going to be the same Bayesian network here, but the parameters are different. In particular, I'm going to consider a single parameter of R given G instead of having P of R1 and P of R2. So now, how do I estimate distribution of this model? So let's begin. So probability of G is the same as before. And now the probability of R given G, I'm just going to count the number of times a particular local configuration shows up either where R is R1 or R2. So D3 shows up once here. D4 shows up 3 times. You have 1 and 2 and 3. So notice I'm counting both occurrences of R1 and R2. And D5 shows up twice here with R1 and here with R2. C1 shows up once, C2 shows up once, C4 shows up once, and C5 shows up once as well. Now I just count and normalize. So I look at all the P's and I count, sum and normalize. And I look at all the C's I count normalized. Okay, so when I have only one distribution that is responsible for two nodes, I simply aggregate their counts and normalize. So this is an important slide. So the more general idea that I want to highlight is this idea of parameter sharing in Bayesian networks. And this happens when the local conditional distributions over different variables are actually the same. And to be very precise about that, I want you to look at the following picture. So we have G, R1, and R2. So far, we've looked at Bayesian networks through the lens of inference, where we know that every variable comes with a local conditional distribution, but we didn't worry about where that came from. It was just there. But now for learning, it matters where it came from. So what we should think about is each of these variables being powered by a local conditional distribution. So G is powered by this table here. R1 is powered by this table. And in the case of parameter sharing, R2 is also powered by this table. So we have a Bayesian network, and behind the scenes, you should think about all these tables which have arrows kind of hooking up and providing juice to each of these variables. And now, if you didn't have parameter sharing, then R1 and R2 would be powered by different tables. Now, this is an important point. When we're doing inference, you should think about that as reading from the parameters. And when you're reading, you don't care whether you have two copies of something or one copy of something because you're getting the same thing. But in learning, we're writing to the parameters from the observed variables. In that case, you need to worry about whether you're writing to one memory location or two memory locations. So the right analogy is you think about in programming, you have pass by reference or pass by value. And in parameter sharing, we're passing by reference. So we're passing this parameter into each of these nodes. And when we do learning, we write back into those parameters, and it matters whether they're the same parameters or not. So when would you do parameter sharing like this? Well, it's a trade-off, and it's ultimately a modeling decision. So by doing this, you aggregate your data, which means that you have more data per parameter, which allows you to get more reliable estimates. On the other hand, you end up with less expressive models. For example, if you had a lot of users, you might lose the ability to personalize if you parameter share. And there's obviously many intermediate points as well, which we won't get to. So let's look at some other Bayesian networks with parameter sharing. So we already looked at naive Bayes before, but just to anchor it in this notation, we have some, let's say we have a genre and we have a movie review, and we have a Bayesian network which generates each word independently conditioned on the genre. And so the joint distribution over everything is equal to probability of under genre of y times for each word, the probability word given of a particular word given y. So the parameters of this Bayesian network are p genre and p word. So now you can think about doing a little exercise of how many parameters are there. So you look at theta and say p genre, well, that's two parameters because two genres. P word, that's 2 times the number of words that number of values that wi can take on. And so that's it. So notice, importantly, that the number of parameters does not grow with L, even though the number of variables in the Bayesian network grows with L. So now we see the kind of the complexities of the parameters and the number of variables to be quite different. You can have a 1,000,000 variable Bayesian network, but you might have only one parameter, for example. That's quite possible. So here's another example, our friendly HMM. So we have actual positions of objects, H1 through Hn and E1 through En. And This should be very familiar by now. So you have HMM, which has a joint distribution, which is given by three distributions: P start of H1 times transition of Hi given Hi minus 1 times, for each variable, the probability of emitting Ei given Hi. Again, the parameters are P star, P trans, and P emit. And you can think about how many parameters are in this Bayesian network. Well, you have the number of positions times number of positions squared times number of positions times number of possible sensor reading values. Okay? Again, there is no dependence on the time window, the number of time steps here, n. And this is useful because if you imagine tracking over a long period of time, you may have 1 million time steps. You don't want the number of parameters to be the same. Okay, so here the training data is going to, again, be full assignments to all the random variables. And later in a future module, we'll come back to the case where in practice, you might only observe the sensor reading, but more on that later. So now let's present the general case. Hopefully the intuitions have already been fleshed out, but I just want to write things down with some formal notation. So a Bayesian network, remember, includes variables x1 through xn. And now we have parameters. And the parameters is a collection of distributions. So I'm going to write that as P subscript D, where D indexes into some set. And for the HMM, for example, big D is start, trans, and emit. So D is just a label, if you will, name. So each variable xi is generated from some distribution, and now the notation gets a little bit, hairy, but it's P sub Di is the distribution that points into xi, and I'm taking that, looking up that distribution by name. So you can think about this more formally as this is just the equation for defining what a Bayesian network is of the joint distribution. So it's a product of the local conditional distributions, but now I'm being very explicit that each variable di, every variable I has a particular distribution that is powering that variable. So the idea of parameter sharing is that di is just the same for multiple i's. Okay, so here is the learning algorithm for general Bayesian networks. So the input is a D-train consisting of full assignments to all the variables x1 through xn. And the output is going to be all these distributions here. So the algorithm is, again, just count and normalize. So what we're going to do is go through every training example, which is a full assignment to all the variables. For every variable in your Bayesian network, we're just going to increment a counter. Okay, so what this counter is I look at which distribution is powering variable I, and I'm going to increment that counter for the local configuration, which is looking at the assignment to its parents and also the value of xi. And then I'm just going to normalize for each distribution and local assignment to its parents. I'm going to set the probability under that distribution of xi given parents to be proportional to this count. Okay, and that's it. So far we've presented this counter normalized algorithm, shown a lot of examples, and hopefully this seems like a reasonable thing to do. But part of you might still be wondering, well, why? Why is count and normalize a reasonable thing to do? And there is a higher principle here, and it's called maximum likelihood. So the principle of maximum likelihood, which is a very old idea in statistics, is that we have our training data here. Okay, so if we look at the product of all examples in the training data, and we look at the probability under the Bayesian network that that is assigned to that data, And notice I'm going to provide semicolon theta here to recognize the fact that this Bayesian network depends on the parameters now. So this is the likelihood of this data given these parameters. And maximum likelihood is saying, I want to tweak these parameters so that this likelihood is large as possible. So this should look a little bit more like what we were doing in the machine learning modules, where we write down a loss function, which depends on parameters, and which is usually a sum over the data, and we try to find the parameters that minimize loss. Here it's the opposite. We're trying to find the parameters that maximize the likelihood, and if you just take a log and you negate it, you actually end up with minimum loss as well. But I will ignore that for now. So intuitively, this is a reasonable principle as well. What you're trying to do is, for every setting of parameters, that gives you some likelihood under the model of the data. And you just want to keep on tweaking that until the likelihood as high as possible. So having said that, now I'm just going to claim that that algorithm, which we called counter normalize, is exactly solving the maximum likelihood objective. So this is really nice because it gives us a closed form solution to this maximum likelihood objective. You don't have to take the gradient of this and iterate and worry about convergence. Also, it's just done. And this is one of the reasons that makes maximum likelihood estimation in Bayesian networks so scalable and intuitive, is that, well, it is scalable and that was a little bit tautological. All right, so I haven't justified why maximum likelihood principle leads to the counter normalized algorithm, but let me just provide you a little bit of a taste of why this might be the case. So let's take this small data set, D4, D5, and C5. So if I write down the maximum likelihood objective, so I have two variables here. I'm going to expand that. Okay, so I have max over theta, and theta really here is the probability of genre, the probability of rating of given that genre is C, and the probability of rating given genre is D. So I have three distributions here that I want to optimize, and I'm just going to expand out based on the definition of a Bayesian network. I have probability of a D given probability of rating for given D. So that is the probability of the first data point times P of D, 5 given D. That's the second data point. And then P of C and P of 5 given C, that's the third data point. So I'm multiplying all these probabilities across all the data points, and that is the probability of the data given a particular assignment to the local conditional distribution. And now I've color-coded them on purpose because what we can do is we can shuffle things around. So if you just look at probability of G, right? So I'm maxing over that, and that shows up in these three places, and it doesn't affect anything else. So I can just pull that out, and I can pull the green apart, which is R given C, and I can pull the blue stuff out, and that's maximizing over if R given G equals D here. So the punchline here is that we can decompose the maximum likelihood objective, which looks like a big tangled mess, into actually subproblems, one for every distribution and assignments to the parents of a particular variable. And now, having done that, now I have just a little local optimization problem here, which is basically solved by in closed form. You can do this. I'm not going to do this for you, but you can introduce a Lagrange multiplier for the sum to one constraint, and you do some, take some derivatives, and you set it at 0, and then you get that the probability, maximum likelihood probability, is proportional to the case here. And in this case, what we will estimate is that the probability of D is 2/3, probability of C is 1/3, and so on. Okay, so let me summarize now. So we've talked about learning in fully supervised Bayesian networks where we're observing instances of all the variables here. So one important concept to take away is this idea of parameter sharing. So we have talked about just a Bayesian network, which an inference doesn't care about where these parameters come from, but we should really think about each of these nodes as being powered by a particular local conditional distribution. And sometimes two variables could be powered by the same distribution. And again, inference is reading from the parameters, learning is writing to the parameters, in which case it matters where these arrows come from. So secondly, we looked at the maximum likelihood principle, which is this kind of high-minded principle that says maximize the likelihood of your data. And we show that this is equal to this very pragmatic and simple intuitive principle of counting and normalizing. And this is the simplicity which makes Bayesian networks, especially naive Bayes, still very kind of practical, useful, and interpretable. That's the end.